All right, so I'm going to continue on section 10.2. And in this section, we're going to introduce another public key crypto system called the Knapsack Cryptosystem. In fact, this is one of the oldest or earliest public key crypto system that was introduced in 1978. And this crypto system is based on the difficulty of solving a classical problem in combinatorics called the Knapsack Problem, or another name for it is called a subset sum problem. So this crypto system was developed by Ralph Merkley and Martin Hellman in 1978. And again, it is one of the earliest public key crypto system. Let's state first what is called the knapsack problem, and then see how it is used. Actually, the difficulty of solving this problem again is actually the basis for this crypto system. In other words, security is based on the difficulty. There is no basically good algorithm in solving this, at least when it was invented or when it was introduced. Then later on, they found actually there is a way to solve this special type of knapsack problem associated with the crypto system that is known as the knapsack public crypto system. So here it is. Here's the statement of the problem. Given a knapsack of volume V and n elements of various volumes, A1, A2, up to AN, where V and A1 up to AN are all non-negatives, and in fact, they need to be positive. Now, the question is, can a subset of these elements be found that will completely fill the knapsack? And here, if we're going to think about this from a physical point of view, that we're going to assume this knapsack is going to be filled with no spaces in between these different objects that we're going to put in. We could restate actually this problem in a different way as a solution of a certain type of equation. Given positive integers A1 up to AN and a sum V, and we want to solve this equation V equal A1 x1 plus A2 x2 up to AN xn, where the values, we're going to solve for the x sub i's, where the values of the x sub i's can be either 0 or 1. 0 means do not include this volume A sub I in the knapsack, and 1 means put it in the knapsack. So in general, in a given knapsack problem, there may be no solution, in fact, or sometimes there is more than one solution. Let's look at a couple of examples. For example, if you take A1 to be 3, A2 7, A3 9, A4 11, A5 20, and the volume to be 22, and you set this equation where you're looking for a solution that consists of xi taking either the value of 0 or 1. You're going to find out actually this has no solution. One way to do this is by trying all possible values of the 5 tuple, x1, x2, up to x5, taking the value 0, 1. There is a total of 32 possible values of the x's. That's just applying the multiplication principle of counting. So it is 2 to the power 5. So it's not bad. In other words, it can be tried. So if you try all these possibilities, list all of them, then you're going to find none actually does give you the sum of 22. On the other hand, if you take V to be 27, you're going to find out there are two distinct solutions. One solution where x1 equal x5 is equal 0, and x2, x3, x4 is equal 1. So you just plug these in, and you will see that they will add up to 27. And another solution where x1, x3, x4, 0, x2, and x5 is equal to 1. And it's not very hard to see x2, 1, x5 is 1, this is 27, and the other 0. Yes, it does satisfy the equation. And these are the only two solutions. So in general, if we want to use the trial and error to solve a knapsack problem with n elements, A1 up to AN for a given volume, V, where we're looking for a solution of xi to be either 0 or 1. This requires, if we want to use brute force method for solving it, it requires 2 to the power n possible values of x1 up to xn. Now, as you can see, for large values of n, this is extremely infeasible. For example, if n is equal 100, this is 2 to the power 100. It's a number even doesn't have a name. It's a very large number, and it is hard to use this trial and error, or what we call sometimes brute force method. However, there are certain sequences of integers, A1 to AN, where the solution for the knapsack problem is easy to find, a very simple method to find. One of these cases is where the sequence A1 up to AN is given by this, A sub j, where we have 2 to the power j minus 1, where j ranges between 1 and n. So when we have this, here's an example with how to actually find a solution for such sequences, which is powers of 2. So if V is 97, and we have 97 is equal x1, so this is 2 to the power 0, then 2 to the 1, x2, x2, and so on, up to 2 to the power 6. Of course, if we have values that give us a number that is bigger than 97, we can ignore all of these, because all of these, we could take their x's to be 0. So we wanted, in fact, the largest to be less than or equal to 97. Now, to find a solution for this, or determine if there is no solution, all we have to do is find the binary, or what we call bit representation, the binary representation, or representation of 97 base 2. And this is given in this case to be the digits of starting from left to right, 1, 1, 0, 0, 0, and so on to 1. And you actually take these are to be the values of your x1 to be 1, which is the very first, the units kind of digit, then x2, x3, x4, and x5 all zeros, and x7, x6, and x7 to be 1. Because this is, you could think of it as actually the binary sum of powers of 2, and whenever we have a power is counted, then we're going to use the x associated with that power to be 1, and if it's missing, means it's not there, means there should be a 0 in the binary representation of the number. So this is one class of knapsack problems that can easily be solved this way. Also, it's not very hard to see that we could generalize. This is more for if the A's are powers of 3 or powers of 4 or powers of 10, means, you know, using the decimals. All right, another class of knapsack problems that are easy to solve is choosing a set or a sequence of integer so that the sum of the first j minus 1 of this integer is always less than the next integer to it. All right, so means let's start with the third integer here. So a3 is going to be actually less than the a1 plus a2 is going to be less than a3. So they're going to be actually increasing kind of rapidly in here. So the condition, we can express it as, which is the first of the j minus 1 integer, for the sum I equal 1 to j minus 1 a sub I. We require this is to be less than a sub j for every j from 2 to n. A sequence that satisfies this property, we refer to it as super increasing sequence. So the super increasing sequence is a sequence of numbers where starting from actually the second term, it's going to be it's going to be one term before that, it's going to be bigger. And the third term is going to be bigger than the sum of the first two terms. And the fourth term is going to be strictly bigger than the sum of the first three terms, and so on. So such sequence, we call it a super increasing sequence. Now, if the A's happens to satisfy this property, it turns out that the knapsack problem can be solved easily. And in fact, there is an easy algorithm that we can apply to solve such a knapsack problem. Here's an example before we describe the algorithm in general. Let's assume we have this equation: 2x1 plus 3x2, 7, x3, 14, x4, 27, x5 is equal 37. All right, the first thing you will notice that the sum of the first four coefficients, x1 up to x4, is actually less than 27. And the sum of the integers from the sequence can be greater than 27 if the one term of the sum is 27. So in other words, we cannot, in other words, include a 27 in order to get 37, we cannot only use the first four terms, we must include actually the fifth term. I'm sorry, we must include the fifth term, which is x5 must equal to 1. Because if x5 is 0, then the other terms, they're gonna not make it to 37. So here it is. So we obtain x5 to be 1. And by substituting x5 is equal to 1, we come up with another equation by subtracting the 27 to the other side of the equation. Then we have 2x1 plus 3x2 plus 7x3 plus 14x4 is equal to 10. Then we repeat this process. So if we add the terms 2, 3, or the coefficient 2, 3, 7, this gives me a 12. And this is actually bigger than the 10. So in other words, we cannot have x4 is equal to 1 in this case. because if it is, and even all the others, it's gonna exceed 10. So in this case, we take x4 to be equal to 0. Now we drop x4, and then we look back at 2x1 plus 3x2 plus 7x3, 17 equal 10. And again, since the sum of 2 and 3 is less than 7, and we wanted to get 10, then we must have x3 is actually must equal to 1. And then we need to combine it with, with either x1 or x2. In this case, we're going to see x2 to end up with 10. So we take x3 to be 1, and then again we form another equation, and then we find that x2 is equal to 1, x1 is equal to 0. So this is the way we actually solve this type of knapsack problems, going from the last x sub n, and either it's going to be equal to 0 or 1, depending on the sum of the previous terms. If it is smaller than the last term, then we include it in, and then we form another equation, and we repeat this process. So in general, to give a general algorithm for solving a knapsack problem for super increasing sequence, first of all, we have a solution. If and only if V is going to be less than or equal A1, A2, up to AN. Because if V is bigger than these, then regardless of what, because we're going to put, the best we can do is to take all the x's is equal to 1. So if when we put the x's all equal 1 and come up with bigger than V, then of course we cannot get to V. So to find the solution with this algorithm, first we find xn by noting that, or taking xn to be equal 1 if the an is actually smaller than or equal to V, and 0 if an is strictly bigger than V. All right, so V is going to be bigger, so we can include an basically. Then we can find xn minus 1, xn minus 2, using the same procedure actually. In other words, we could do it what is called recursively. Or we can actually write what is the x sub j, it's equal to 1 if V minus the sum of the terms I equal j plus 1 up to n xi ai is bigger than or equal to a sub j. Now remember, these are the terms which we already determined, these x from j plus 1 up to n, as we're going backward. And we take 0 if this difference between V and the sum of the first from j plus 1 to n is actually less than a sub j. The proof of this is actually why it works is by contradiction. So if xn is equal to 0 when V is bigger than or equal to n, means the opposite of what it's supposed to be, then we're gonna reach a contradiction here. Then we look at the sum from I equal 1 up to n, a sub I, x sub I. Since we are taking xn to be 0, then we can drop that and take all the values of the x's, the remaining x's, to be equal 1. That's the largest we can take, all right? And then this sum is going to be less than or equal a sub I, because we include all of them, I equal 1 to n minus 1. But because the sequence is super increasing, we know that this sum is going to be strictly less than the term that comes after, which is an. But we have an is actually less than or equal to v, and this contradicts that actually the sum should be equal to v. Similarly, we treat the for the x sub j in a similar argument. We see it actually leads to a contradiction. So in other words, using this algorithm, we can see that the knapsack problem is very easy to solve. Now we come into the crypto system that is based on this difficulty of solving a knapsack problem for non-super increasing sequences. The idea is to take as a key, as the what we call the secret key, to be actually a super increasing sequence, and then using a way to associate with this a sequence that is not super increasing, and then create a kind of a knapsack problem using the non-super increasing sequence. So let's see how this actually does work. So a typical user first choose a super increasing sequence, A1 up to AN. Then a modulus, because we're going to be using modular arithmetic to do the calculation, M, and a positive integer is chosen, this M, such that M is bigger than twice AN, and AN is the last term of this super increasing sequence. And also we're going to choose something we call a multiple A, and this A is a number between 0 and M, and it is relatively prime to M. And we're going to see, why this condition on the greatest common divisor. So also to be chosen. So again, we're going to choose a super increasing sequence, A1 to AN. We're going to choose a modulus, M, and this M satisfies the inequality to be bigger than 2AN. So it's, relatively speaking, is going to be large. And then we're going to choose what we call a multiple, A, that's a number between 0 and M and relatively prime to M. The choice for A to be relatively prime to M, so that this congruence equation, AX congruent to 1 mod M, has a unique solution. And let's assume that this solution is C. The second step is to use the A1 up to AN sequence, which is super increasing, to come up with another sequence that is not super increasing. And this sequence, we're going to denote its elements by B1 up to Bn, where each term in the sequence is given as the number A, that the multiple A sub I mod M, for every I between 1 and N. And of course, this is reduced mod N, so these are going to be between 0 and M. This new sequence that we formed in general is not super increasing, doesn't satisfy the super increasing property, or we actually insist of it not to satisfy the super increasing property. Then the user actually keeps secret, the person who's gonna receive the messages, all right, keep secret the original sequence, A1 to AN, and also M and A, but publishes the B1, B2 up to Pn in a public directory. So this is the public key, is going to be this sequence B1 up to Bn. So anyone wanted to send a message to this person, they're going to use the public key, and then encrypt a message and then send it to as an encrypted message, and when the other person with the secret key A1 to AN and the M and the A will de-encrypt. And let's see how this is actually is done. So the way it is done is, first we're gonna convert the plain text message into a string of zeros and one. And we're gonna use the binary representation given equivalent to letters as given in the textbook in page 211. The string of zeros and one then is split into n blocks and of binary digits, with the last block being filled out with ones at the end if necessary, because we need all to have these blocks of the given length n. Then the public encrypting sequence B1 is used to transform a given plain text block that has these numbers or these binary representation x1, x2 up to xn into this sum. So this is going to be zeros and ones. So we form this knapsack problem. Actually, we just multiply B1 by x1, and then we come up with the sum. So this sum is going to be actually sent to the person that has the A1 up to AN as the secret key. Now, the problem of obtaining the plain text from S, now we need to find what S is. In other words, the recipient is going to receive this S, all right, which is a sum, and is equivalent to solving a difficult knapsack problem, because the sequence B1, if someone intercepted, then they have to solve the knapsack problem with these P's, which is not a super increasing sequence. However, the private key can be used to convert this hard knapsack problem into an easy one. And the way it is done, now we know the values of C and M. So the recipient computes S prime, which is equal to C multiplied by S mod M. And then, of course, we reduce S prime to be between 0 and M. Now, let's see what is this is actually is equal to. C, which is the number, which is, again, it's a private. And then we multiply by S, which is the sum using the B's. And when I multiply through, and now remember that we actually have B1 is equal A1, B2 is A2, and so on. Also, we have CA, all of these is equal to 1. So in other words, S prime, it becomes a knapsack equation with increasing, a super increasing sequence A1 up to AN. And this is easy to solve. And now by solving this, then we can recover actually the original sequence, the original text. Yeah. So once again, this crypto system, its security, or it's based on a failure of or the inability to solve a particular type of problems in competitors. All right, here is an example. Again, there are a couple of examples from the textbook I chose in here, because the calculation, again, it requires a lot of computations. So let's assume that we chose the super increasing sequence which is a 3, 5, 11, 20, 41, and the modulus is 85. And the multiple, that is a number relatively prime to m, is 44. Now, each member of this super increasing sequence is going to be multiplied by 44 and reduced mod 85 to produce another sequence, which is non-super increasing, which is 47. So these are the B's, the 47, 50, 59, and so on. And this is going to be actually the encryption key, which is going to be public. And the user actually publish this sequence. Now, someone, let's say, assume we want to have a plain text message that is help us. The first thing we're going to convert the letters into binary equivalent, and each binary equivalent to each letter consists of a length 5 binary string of zeros and ones. So here's the message using zeros and one. And now we're going to use each block in this message 0, 0, 1, 1, and multiply this by the B's. All right. And then we obtain the first sort of what it corresponds to the first block in the message. And then we do it for all other, parts, the zeros and ones in here, multiply them again by 47, 50, 59, and so on. And now this is the sphere text message is going to consist of these numerical values. Now we need to find the number C, which is a solution for 44x congruent to 1 mod 85. And the solution of this, there is a unique solution mod 85, which is a 29. And now by multiplying 108 by 29, we get 72, and then the corresponding knapsack problem with this, it's going to be set using the secret key, which is 3, 5, 11, 20, and 41. And upon solving this, we're going to find actually the original block, the first block of the original message, plain text message. All right. Here is another example. That is, if we make the take the n, all right, blocks of actually bigger length, n equal 10, then the message is going to be divided in this form. Each block of zeros and one is going to be partitioned into length 4 blocks. And again, we using the same sequence and taking a different value of m. We change m and a, and upon doing the same calculation, we're going to find actually this is harder actually to solve. Means if than the original one. So in other words, increasing the blocks makes solving the knapsack problems actually harder. The next thing it turns out many years later, the knapsack problem was actually attacked, and this as a public crypto system means it's not used anymore. The person who actually produced a solution for the knapsack problem associated with this kind of crypto system was done by Adi Shamir in 1984. And the solution he introduced is actually does not only without knowing, means he could solve the problem without knowing actually the decryption, the secret key. All right, I'm going to leave the details of how Shamir, actually they are in the textbook, they are not given the full details of this. However, it is kind of more or less, it's like a wave handing way of doing this, but not in any mathematically sound way. All right, so I'm just gonna leave it out. All right, in other words, they are just indicating how this is done without going through the details of finding these pair of numbers, which we call U and V. All right, so this is the second section of chapter 10. I have another section, chapter 10.3, which is again is going to be a short section. So I'm just going to stop writing.